So in this lecture, I'm going to be giving some examples of this theorem. So this theorem is that if we have two angles, alpha and beta, and we're rotating around 2 points, A and B respectively, that the product of these two rotations is the same as a rotation about some point by alpha plus beta, unless alpha plus beta is an integer multiple of 2 pi. And in that case, it's a translation. So the first two examples I'm going to do are fairly easy results in geometry. And so we'll see that. But the point is that we can obtain these results using translations and rotations using that theorem we just talked about. So the first example, you have a triangle ABC, and we want to take midpoints of two of these sides. We're going to take the midpoint opposite point B here, so the midpoint of side AC, and I'm going to call that M sub B. And then I want to take the midpoint opposite C here, the midpoint of AB, and call that M sub C. Then I want to look at the segment going from MC to MB. And the claim is that these two lines, or line segments if you want, are parallel. But as lines, the line going through these 2 points and the line going through these 2 points never intersect. And we want to show that this distance from MC to MB is half of the distance from B to C. So this follows fairly easily by looking at these two triangles, the small one up here and the big one, ABC. These two triangles are similar. And by using ratios of corresponding sides, then we can see that the segment from MC to M sub B is half the length of the segment from B to C. That's because this is half of this length. And we can look at these two angles and see that they're the same to deduce that these two lines are parallel. Again, we want to do this a different way. We want to use translations and rotations. And I'm going to start with a certain function, not one you would necessarily think of right away, but it comes to mind if you look at it a little bit and have some experience. So the experience is what we're after now. So here's a product of two rotations. I'm rotating about MC by pi, and then I'm rotating about M sub B by pi. And what I want you to think about is what happens to B when I do these rotations. I want to take B, apply this rotation to it, and then apply this rotation to it. So give some thought to that. What's happening to B after I do those two rotations? So B gets mapped to A by the first rotation. You're rotating around MC counterclockwise by pi, so B is going from here to A. That's what the first rotation does around M sub C. And then I want to apply a rotation around M sub B by pi, and that's going to take A to C. So A is going to go to C. So F of B is going to be C. It's going to be a rotation around MC first, followed by a rotation around M sub B, and that's going to take B to C. Now let's think about the theorem we have. The theorem says that if I rotate by the angle pi twice, and the sum of those angles is 2 pi in this case, 2 pi is an integer multiple of 2 pi. It's 2 pi times 1. So that means the product of these two rotations should be a translation. So F is a translation. Here again is the end of that theorem. It said if the two angles add up to an integer multiple of 2 pi, we get a translation. So we can conclude that F is a translation which moves B to C. What does that mean about F? It takes every point in the direction of the vector BC, the length of the vector BC. Every point's going to move in this direction, this amount. This direction, this amount. No matter what the point is, it's moving in that direction, that amount. So the same direction as BC and the same length. Okay, so F as a translation means it's moving all points the same distance as it is from B to C in the direction of the vector BC. So how can we use that? Well, next we're going to look at what happens to M sub c under these two rotations. Let me just give that a name first. I'll call that MC prime. So this is the result of applying F to MC. In other words, I'm going to rotate MC about MC by pi, followed by rotating about M sub b by pi. So why am I interested in looking at MC? Well, one point is that this is easy to evaluate. When I put an MC here, I'm rotating around MC. It doesn't do anything. M sub c is the center of the rotation, so every point gets turned around M sub c, and M sub c is not going to move if you do that. So the first rotation about M sub c by pi of M sub c is just going to take MC to itself. So this stays where it's at. Now we want to rotate around M sub b by pi. So that means we want to go around M sub b by pi. We'll take this to go 180 degrees this way and end up over here someplace. So we want to rotate MC around M sub b by pi. Just going to swing this around. So we'll end up over here. What do we know? That since we rotated M sub c about M sub b and got M sub c prime, we know that this distance should be the same as this distance. So these two distances are the same. The distance from MC to MB and MB to MC prime. We also know that these 3 points are in a line because this was a 180 degree rotation. So we have these are the same length, this distance and this distance. And these 3 points, M sub c, M sub b, M sub c prime, are all collinear. There's only one other observation I really need to make, and again, that's because F is a translation that moves B to C. So if it takes B to C, it's apparently taking MC to MC prime, same translation. So that means that this is moved the same direction and the same amount as going from B to C. So that's going to mean that these two vectors, the vector MC, MC prime, is the same as the vector going from B to C. So what does that mean? Well, for one thing, it means that this is parallel to this. So that's give me the first thing we wanted, that MB, MC prime is parallel to BC. These are going to be parallel because the vectors are equal, so they're going in the same direction. The other thing we wanted was that the length of MB, MC was at 1/2 of the length of BC, and we can see that because this length was half of this. Remember these two, this was the same length as this. So MC to MB is half of this distance, and this distance has to be the same as this distance because these two vectors are equal. So that means this is half of BC. So we get, in fact, that the segment MC to MB is 1/2 the length of the segment from B to C. So that finishes problem 1. Let me look at problem 2. Problem 2, we have an arbitrary quadrilateral. And what I want to do is take the midpoints of the sides. And what we're trying to show then is that these midpoints, if you join them, the edges always form a parallelogram. Now, I might have been a little deceptive here. That does not mean all 4 of these are the same. That means that the opposite sides are the same length. And the opposite sides are going to be parallel. So it's not too hard to see this from the previous problem. In fact, that's how we want to do it. We did the previous problem with translations and rotations. So we can use that result for this one, and that would mean that this follows then from translations and rotations as well. So the idea is simply to draw the segment BD here, and that notice that this gives me a triangle on the top, like we had a triangle in the previous problem. So we have this triangle on the top, where this is the midpoint of this side, midpoint of this side. We draw that line, and in the previous problem, we saw that this line here was parallel to BD, and it had half the length of BD. And now if you look down here, here's another triangle, So we have the midpoint of this side, the midpoint of this side. We draw a segment between them. So by that same problem, problem 1, we see that this is half the length of BD and is parallel to BD. So this is parallel to BD. So since this side and this side are parallel to BD, then they're parallel to each other, and they also have the same length because they're each half the length of BD. And that's enough to make this a parallelogram, but you could draw a C in here if you want and convince yourself also that this and this then are both half of the length of AC and parallel to AC, giving the same result that these two sides are parallel and equal in length. So that's how we finish this problem, just by using the previous problem. And since that followed from translations and rotations, this does as well. The last example I want to do today is going to involve a generalization of this theorem that we've been talking about. So something that's true, that's more general, says more. That theorem is the following. Instead of just having 2 rotations, we're going to imagine having n rotations about n points P1 through Pn. And the conclusion is basically the same, that the product of these rotations will be a rotation about some point Q by the sum of the angles if the sum of the angles is not an integer multiple of 2 pi. And if the sum of the angles is an integer multiple of 2 pi, then the product of these rotations is a translation. So you might imagine that this is not so difficult to show from the previous theorem up there by simply grouping this, taking these two first. The product of these two rotations will be a rotation by the sum of the angles alpha 1 plus alpha 2, and then take another rotation. So this will be one rotation now, and then take the next rotation and group those two together, and that will give us the 3 rotations are going to be a rotation, and so on. There's one difficulty with that argument, and I'll explain it with an example here. And I'll also show you how to get around it. Suppose we have 5 rotations, and we're trying to use the previous theorem to say that this theorem is true by first grouping these 2 rotations together, multiplying this out, and seeing what it is. Well, notice these angles add up to 2 pi, 2 pi times 1. So the previous theorem would tell me that this is a translation. And right away, we see I have some difficulty because now I got to take a translation times a rotation if I continue this. And I don't know what a rotation times a translation is because the previous theorem didn't address that. So how would we handle a situation like this in this theorem by using the previous theorem? It seems like just simply multiplying 2 of these together is going to give us a translation, and that's going to make this difficult to use. So the idea is to rewrite this rotation, say, around b by pi. And I'm going to do that as follows. I'm going to imagine rotating around b by pi halves, so taking every point in the plane, keeping b still, but turning everything else around b by pi halves, and then do it some more, do another pi halves. That's the same thing as rotating around b by pi. So this is the same as this. I'm rotating around b by pi halves, followed by continuing to rotate around b by another pi halves. So that's going to be the same as a rotation around b by pi. And now I'm going to group these a little differently here. I'm going to go ahead and group these 2 together, what's on the right here together, and then group all these other ones over here. Now just to clarify, the product of rotations you can think of as being a product of matrices. You can't commute matrices, but you can use the associative property for matrices and group them. So I'm taking the product of these matrices, and I'm going to group them in the order where I'm taking the product of these 2, then the product of these 2, followed by the product of this one, and then this one. Okay, and then the last product. So when I take the product of these 2, I have a rotation by 3 pi over 2. Now I come over here. The sum of these 2 is 3 pi over 2. So that's going to be a rotation about some point by 3 pi over 2. Now when I take that rotation about some point by 3 pi over 2, multiply that by a rotation about some point by pi, I'm going to get a rotation about some point by 5 pi over 2. And then I'm going to get a rotation about some point by 7 pi over 2 when I multiply by this next rotation. So I'm just using the previous theorem, the first theorem we had, where we just add the angles. These aren't multiples of 2 pi, so I can just add the angles. I get 3 pi over 2, and then 5 pi over 2, and then 7 pi over 2. So now I know this is a rotation about some point by 7 pi over 2. This is a rotation about some point by 3 pi over 2. 7 pi over 2 and 3 pi over 2 add up to 10 pi over 2, or 5 pi. That's not a multiple of 2 pi. It's not 2 pi times an integer. So this will be a rotation about some point by 5 pi. Notice this adds up to 5 pi. So that is what we want. It's a rotation about some point by 5 pi. And so that is giving us the conclusion we would want in this theorem. And all I did was really to reuse the previous theorem and rewrite r sub pi of b in the right way here. And they didn't have to be pi halves here. If you wanted to make sure it didn't add up to integer multiple of 2 pi, you could do something crazy like square root of 2 over 2 times pi here, and 1 minus square root of 2 over 2 times pi here. Just some angles here that add up to pi. But you break up r sub pi b like that, and then just group them correctly, and then you'll end up getting that this is a rotation about some point by 5 pi. Okay, so that's roughly how you would go ahead and prove this in general. And you just have to sometimes worry if things add up to a multiple of 2 pi, but you can get around that by doing this trick that I did here. Now, I want to go ahead and talk about an even more general theorem. So here I have rotations around A1 through AN by alpha 1 through alpha n, respectively. But I also have some translations by B1 through BK. And I want you to imagine doing these rotations and translations in any order. So just go ahead and do them in some order, but any order is okay. I don't mean they have to be done in this order. I can do a rotation around A3 by alpha 3, followed by a translation by B1, followed by a rotation around A1 by alpha 1, and so on. Just use all of these at least exactly once. So we're doing N rotations and K translations, but in any order. Then the product of those rotations and translations will be a rotation about some point by the sum of the angles, provided the sum of the angles is not an integer multiple of 2 pi. And if the sum of the angles is an integer multiple of 2 pi, then f is a translation. Now this theorem follows from the previous theorem if you look at what we did for the homework 7. So in homework 7, we saw that we could rewrite a translation as a product of two rotations. So if I take each of these translations we had and rewrote them as products of rotations, then this f we're defining here would actually be just a product of rotations. And so we could use that. So you'll have to look back at what the rotations were and such, but that's what's happening there. So we have what we want. We have that this theorem, and now we want to apply it. There's one other comment I should make, and that is if you take a rotation, say these angles add up to 5 pi like I had on the previous slide, if these angles add up to 5 pi, and I'm rotating around C by 5 pi, notice you're going around C, you're rotating everything 2 pi more, and then one more. So rotating around C by 5 pi is the same as a rotation around C by pi. So when I take the sum of these angles, if they're more than 2 pi, you can subtract 2 pi from them. So again, if this was adding up to 5 pi as in my example here, and C was some point I'm going around C by 5 pi, would be the same thing as going around C by pi. So the last example I want to do in this lecture is not something you would normally see in a geometry class, but it has a fairly simple argument using what we've been talking about. So let's look at this. We're starting with n points. They can be anywhere, but they have to be an odd number of them. So we have an odd number of points. And then we're going to take any point. So we want to think of these points P1 through Pn as being fixed, but take any point then and start rotating around the points P1 through Pn. So first go around P1 by pi, then go around P2 by pi, then P3 by pi, until you get done with all endpoints. And then what we're going to do is rotate around all those points again. Rotate around P1, wherever you were after you did the first rotations. Rotate that around P1 by pi, and then P2 by pi, all the way up to Pn by pi. And the claim is that after you do the rotations around P1 through Pn twice, you always end up back where you started. Now it looks a little bit more impressive if you see this in action. So let me go ahead. Here are our 3 points, P1, P2, and P3. And I have a point A0 here that's going to apparently be out of the picture in a second. And what I want to do is to rotate around P1 by pi. So maybe I can keep that A0 there. I'm going to go ahead and take this A0 and rotate around P1 by pi. And now I'm going to rotate around P2 by pi. So that's going to give me A2. And now I want to imagine taking A2 and rotating around P3 by pi. So that's A3. Now I want to point to A3. The laser's going to get in the way, I guess, and make A0 go away if I do that. So maybe I'll need to point some other way. Let's see. How can I do this? Here, I'll just point. Okay, so I'm pointing at A3 now. And what I want to imagine doing is taking this result that we just got. We rotate around P1, P2, and P3, got to A3. And now we're going to do that again. We're going to take A3 now and rotate around P1, P2, and then P3. I'm going to fit in here a little bit better in a second. Okay, let's rotate A3 around P1. That takes me over here. I'm going to rotate A4 around P2. That takes me over here. And now I want to rotate A5 around P3. We end up back at A0. So that's what the theorem is saying, that we're going to end up back at A0. So it's not completely clear why that would have happened, right? So here's what we had. We went around A0 and got to A1 here, then to A2, and then to A3, and then around P1 again, and then P2 again, and then P3. Okay, let me comment that it's a little misleading here. This segment, A2, A3, is not under or over the segment from A0 to A5. So this is a little bit shifted here. This is a little bit under the line, and this is a little bit over the line. It's just coincidence that they seemingly matched up. So this is what we were trying to show, that we start at A0, we end up at A0. And let me give you the simple argument for this. We're going to look at what the function was that took A0 to A3. This was a product of rotations. We went around P1 by pi, that took us to A0 to A1, followed by taking a rotation around P2 by pi that took us to A2, and so on. And here we ended up at just P3, but we could have an odd number of points in general, and we're going to end up at some point in the end. In this case, it was A3, after we do each of these rotations. Okay, so what does our theorem tell us? We add up these angles. We're going to have n times pi, because we have n rotations here, each by an angle of pi, so we end up with n times pi. N is odd, so it's not 2 pi times an integer. That would be something even times pi. So n times pi is not an integer multiple of 2 pi. So this is a rotation by our theorem about some point that I'm going to call just p. So f is r sub p pi. I put just pi here. Why? Well, again, if I had a n times pi here, like 5 times pi, you're just going ahead and rotating around p twice completely, 2 pi twice, and then there's another pi. Just like I was talking about a second ago. If it was 3 pi, that would correspond to rotating around once by 2 pi and then another pi. So rotating around p by n pi, since n is odd, is the same thing as rotating around p by pi. So that's what's going on with f. So in other words, Since f took a0 to a3, that must have been the same thing as rotating around p by pi from a0 to get to a3. So what happens if I do this process twice? So I go ahead and take f, apply it to a0, and then I do f again, go around p1 and then p2 and so on. Well, then I'm going to be taking a, rotating around p by pi, that's f, and rotating around p by pi again. So it's just doing that rotation twice. It's doing f twice. So again, f was all these rotations, which is the same as just one rotation. So I'm just taking a, rotating around p by pi, followed by rotating around p by pi again. As we talked about before, this is just rotating around p by 2 pi then. So you end up back where you started. If you rotate around a point by an angle and another angle, you just sum those angles around p, right? You're rotating around p by pi, then p by pi again. You're going to end up back where you started. And that's what we're doing. We're taking f and applying it to a, and then we're going, that gave us a there, and just applying f to that again, and we're going to end up back at a. So the fact that the product of these two rotations of a is equal to a no matter what a is saying the same thing as this problem, that we're just rotating around a point by the same point by an angle of pi twice, we're going to end up back where we started. Now it might be clearer to see what's going on if I told you where p was in this picture, so let me do that. So imagine you're taking a quiz or test and I said, okay, we've gone through this problem, where is p? Well, p is on a segment going from a0 to a3, because why? Well, because if you take this, it gives you a3. So r sub p of a0 is the same thing as a now. If you take r sub p of a0, you're getting a3. So that means that a0, p, and a3 have to be on the same line because you're rotating around p by an angle of pi. But also because a has to be the same distance to p as a3 is at the result, you're just going to have p is right in the middle of that. It's the midpoint of a0, a3. So I drew a black line in here again because the line that looks like it's going from a3 to a0 that's in red is not really there. That was the line going from a5 to a0, and it just looks like it's part of going from a3 to a0. But a3 again is a little above that line. So I went ahead and drew in black here the line going from a0 to a3, which wasn't really in the picture before, but the midpoint of that is p. So p is the midpoint of a0, a3. In any case, this simple argument here, that the product of these rotations is a rotation about a single point by pi, gives you that if you do this process twice, you'll end up back where you start. And this is fairly general, just have to have an odd number of points. They can be anywhere in the plane, and then A can be anywhere in the plane. And you just do this process twice with A, and you end up back where you started. So I'll finish this lecture here.